Welcome back. So we are learning about the Thevenin theorem and solving the linear circuits, okay, using Thevenin theorem. And now we are going to look at the examples that contains basically both dependent and independent sources. So earlier, first we learned about how we can analyze a circuit with dependent sources. Then we solve the circuits with independent sources, okay, only independent sources, okay. And we learned that basically for the only independent sources, we need to introduce the as external voltage source. Why external voltage source? Because circuit cannot self start, okay. And then we find the RThevenin based on that, okay, like VP over IP. If we have only dependent source, we can do it directly, okay. So now we have a circuit, okay, that contains basically both dependent and independent. So for this case, we will revert back to the original approach. Okay, we will remove the load and we will calculate basically RThevenin using this approach. We will calculate what is the VThevenin across that branch. Then we will make it short circuit. Okay, and we will calculate what is the short circuit current. Okay, and then by using open circuit voltage or basically VThevenin voltage by making the load open and I short circuit by making it short, we can calculate basically the Thevenin resistance for that case. For this case, what are the targets? Find VThevenin and find the short circuit current at that load point. Once we have those, we can divide them to get the RThevenin value. So let's understand this with the help of an example here. So we look at this circuit. We need to find the V0. V0 is basically the voltage drop, okay, across this 1 kilo ohm here. So in this circuit, we have a dependent source and also we have an independent voltage source. So it's a combination of both. So because we have an independent source here, so the circuit is not self-starting. So that's why we don't need to put up a separate source, okay, like we did for the only dependent cases. Okay, so we will apply the basic approaches here. Okay, our target is what? To calculate basically RThevenin, okay, and VThevenin actually. So RThevenin is basically VThevenin divided by the short circuit, okay. So we need to find this thing, we need to find this thing, okay. So once we know this, we can find the RThevenin. So once we have RThevenin, we can get the Thevenin equivalent circuit. So what is the Thevenin equivalent circuit? Take the load. So my load is actually 1 kilo ohm. But if you remember the earlier example like we did, if we make this open circuit here, no current will be flowing through this one. So we can make this as a part of load actually. Okay, just to make our analysis simple. So this is 1 kilo ohm, this is 1 kilo ohm. Actually, we just want to get the output voltage here. And now the next target is what? Get basically RThevenin and VThevenin. Okay, and RThevenin will be found using this way. Okay, so let's do that now. We cannot find like RThevenin, okay, by using the earlier approach because you have a dependent source here. So we are not sure, like we know that voltage source will be short circuit, current source will be open circuit. But for this case, we are not sure, okay, whether like we can make it short circuit or open circuit. That's why we use basically this approach here. Okay, so first step is draw the circuit without your removed load components. So if we redraw the circuits, how it will look like? Let's do that. Okay, so I have a dependent voltage source of 2000 ix. This is 1k, then this is 2k, then I have a voltage source here which is basically 12 volt, then I have this 2 kilo ohm here. So this is the ix flowing through this one, and here we remove our load, right? So basically this is a point from where we need to calculate the open circuit voltage or Thevenin voltage. Okay, first. Second, okay, we will redraw the circuit one more time. So let me just do that again. So we have this resistor 1 kilo ohm, we have this 2 kilo ohm resistor, we have a voltage source with a value of 12 volt, and here comes our 2k ohm. This is the current ix, okay, and we remove the load at this point, right? Now we will make this point short circuit, okay? And find what is the current basically flowing through this one. This is the short circuit current. Okay, so this is the circuit to find the short circuit current, and this is the circuit to find the Thevenin. So we will draw the two equivalent circuits. Okay, Thevenin will always be open circuit voltage. Current always flow through a short circuit. Like if you have an open circuit, current is zero. So we will make the load removal point as short circuit and find the current. Okay, now we have a simple circuits here. You can apply the different techniques whichever you like to analyze this circuit here. Okay, so what we can do here, so if you look at this circuit, for example, if I try to apply the nodal here, okay, so I notice basically we got a super node here, right? So we have basically a super node here. Where is that super node? So this is my super node, right? So let's call this like V1, this is my V2, and this is my V3. So V3 is basically Thevenin, right? So if you find V3, that will be equal to Thevenin. All right, so supernode, what is the supernode equation? That will be V2 minus V3 is equal to 12, right? Then let's write the KCL at the supernode. So from V2, which current is leaving? This current is leaving. What will be that? V2 minus V1. What is V1? 2000 of Ix divided by 1K, right? Then this current, what will be that? V2 minus 0 divided by 2K. Okay, then this current, what will be that? V3 minus 0 divided by 2K is equal to 0. Okay, so this is the KCL at the supernode equation, right? So basically Ix is the current flowing through this one, right? So what is Ix dependent variable here? That is basically V3 divided by 2K, right? So we can put that here. Okay, so that will become basically V3 divided by 2000. So how the equation will look like? V2 minus 2000, 2000 will be cancelled. So I have basically V3 divided by 1K. Then I have V2 divided by 2K. Then I have V3 divided by 2K is equal to 0, right? So further, what we can do here, we can simply multiply this whole equation, okay, with the 2K to get a simplified form. What will be that simplified form? Okay, that will become 2V2 minus 2V3. This will become plus V2. This will become plus V3 is equal to 0. Okay, or 2V2 V2, that will become 3V2 minus 2V3 plus V3, that will become V3 is equal to 0. So this is my equation, right? So I have two equations and two unknown, V2 and V3. Okay, so we can solve basically uh, these two equations, okay, and that can give us a value of basically voltage V2 and V3. And once we have the value of V3, that actually will give me the Thevenin value. Okay, so if you simplify this one, okay, so the values V3 will comes out to be basically 6 volt. Okay, so V3 after simplification comes out to be 6 volt. Okay, like solving these two equations. So it means my Thevenin is basically 6 volt. So we got this thing here. Okay, now let's again, like I apply the nodal analysis here. If you are comfortable, you can use any other technique. For example, mesh, whatever. Target is to find the voltage drop here. Like we can write the two mesh equations here. Okay, if you know the value of the current flowing through 2 kilo ohm, so V3 will be 2K multiplied with that current. So like mesh is all there, superposition is all there. Okay, you can use whichever technique you like. The target is just to find the voltage drop here. Now let's come to the second part. Okay, now we need to find basically the current source here, right? Okay, so look at this circuit. We want to find the short circuit current here, right? So one thing that we can notice here, this short circuit branch is basically in parallel with this 2 kilo ohm, right? So when 2 kilo ohm is in parallel with 0 ohm, which is short circuit, this will become 0, right? So, or in other words, for example, if some current is coming from here, current always follow a low resistance path, low impedance path actually. So all the current basically will flow through short circuit path, okay? No current will go through 2 kilo. So it means this part of the circuit can be just simplified to a simple 0 ohm or simple short circuit. Like 0 ohm parallel with 2K will become just simple 0 ohm or a short circuit branch. Okay, so basically this will be 2K. So when this becomes 0, actually we have a dependent variable here, Ix. Okay, so actually no current will flow through this 2K here, right? Because all the current is going through this way. So it means the value of Ix will be 0. If the value of Ix becomes 0, it means what will be this dependent source? 2000 times Ix, this will become 0. So 0 volt means what? 0 volt means a simple short circuit. So we can replace this dependent source with a short circuit also. So we have only a 1K here. Okay. So this will be our more simplified circuit. Okay. And our target is again just to find the current through this branch here. Okay. So I have basically 2K and 1K in parallel, right? So 2K parallel 1K, what will be the value? 2 times 1, 2 divided by 2 plus 1, 3, right? 2 over 3. So what is 2 over 3? 2 over 3 is just 0.66, right? So this value is basically 12 volts. So 2K parallel with 1K. So I can basically redraw this circuit that will be parallel. 2 times 1, 2, 2 plus 1, 3. So basically 2 over 3K. And I have this voltage source here. And this is basically my point. So this is 12 volt. So what will be basically, now we got very simple circuit. So short circuit current will be 12 divided by 2 over 3K, right? So 12 divided by 3 over 2 over 3K, this will give me what? This will give me 18 milliampere, right? There is a small mistake here about the polarity. If you look at the original circuit, what is the polarity for the original circuit? Plus and minus, okay? So this is plus and this is minus. Plus, minus, plus, minus. So basically current will be flowing, okay, through this path, right? So actual, we want to calculate this one, short circuit. So I short circuit will be basically negative. Okay, so I short circuit comes out to be minus 18 milliampere. Okay, so we have the value of current, we have, okay, the value of the voltage. So we can find basically the R Thevenin. Okay, so what will be the R Thevenin? Let's put up the numbers here. V Thevenin comes out to be 6. I short circuit comes out to be, what is the value? Minus 18, right? So basically we will choose the magnitude of that. So 18 milli. Okay, so that will come basically 1 over 3 milli will go to the kilo, right? So it will become just 1 over 3 kilo ohm. Okay, so we can use basically the magnitude of the current to calculate the resistance, because the resistance cannot be negative. So this negative is just depicting the direction of the current. So it means our R Thevenin becomes equal to 1 over 3 kilo ohm. Okay, so this way we can basically analyze this circuit, okay, to find the desired equivalent circuit voltage. Now we have our equivalent circuit voltage. Our target was what? To find the V naught, right? So how we can find V naught here now? Okay, simply, like, this is a simple circuit. The easiest way to find the output here is simply using the voltage divider, right? So V out is basically what? This voltage, this resistor divided by the total resistance. What is the total resistance? 1K plus 1K plus 1 over 3 times the input voltage, which is basically 6 volt, right? So if we simplify this one, okay, we can get our answers for the V naught. Okay, so that will be basically what? 2 1 plus 2 2 2 plus 1 2 plus 1 over 3. Okay, so 1 over 3 is basically 0.33 plus 2. Okay, and multiply with the 6, right? So it comes out to be 18 over 7. Okay, or 2.57 volt. Okay, so that will be basically our output voltage. So this is how we can analyze the circuits, okay, with the dependent and dependent source and the independent sources. Thank you so much.